Hello everybody, this is Peter Wagner from the German Aerospace Center, and I welcome you to my presentation about action points in human driving and in SUMO. This talk is based on a poster I presented at TRB this year, and believe me, this feels like from another era. Of course, this has not been done by me alone. I have teamed up with Ronald Nippold and Jakob Erdmann. Let us start with driving. Of course, as you all know, the driver models in SUMO and elsewhere are just that. They are models. Real drivers are a bit different, although on the surface it does not look too difficult to come up with a decent model. You just need a function that maps input like speed, distance, and so on into acceleration, and off you go. Most models assume a time-continuous process, which is usually modeled as a differential equation, and various approximations exist to this, such as a simple Euler time discretization here that is used in SUMO and in many other software. This is a long story, and to do it in this manner is not the only way how it can be done, but real driving seems to be much jumpier than what is assumed by these differential equation models, and this is just the domain of the action point models. The idea behind action points is quite simple. Most of the time the driver does nothing, and from time to time she changes acceleration or the steering wheel angle for that matter to a new value. In this manner, the driver reacts to changing conditions. These points where this happens are the so-called action points, and they have been first observed in 1962 by Barbosa and Todosiev. I've brought one example with me. To the left, you see the time series of the throttle obtained from a real drive. If you look careful, you may see the jumpy throttle. However, the plot to the right displays this more definitely by showing the frequency distribution of the jumps in throttle, and this peaks at 0. Please note the logarithmic scale on the y-axis. By looking into the data, it can be inferred that in about 90% of the cases, throttle does not change in subsequent 0.1 second intervals. What causes the action points? The basic idea is that there must be a cause, and the most successful idea today is to assume perception thresholds. A simple example might be if the distance is smaller than the critical distance, then you start braking. This establishes a very simple threshold, so to speak. You certainly recognize this is a simple car following logic, and the time discrete models are in a certain sense similar to this. However, real perception thresholds are much more complicated. I will give an example in a moment. Note also that accelerations cannot really jump. Cars are heavy objects, so as a comfortable acceleration jump, the so-called jerk, is 2.5 meters per second cube, and in data this jerk rarely exceeds 10 meters per second cube. Here are the promised perception thresholds, a lot of them. They are an important ingredient in these psychophysical models, and the most famous one of those is the Wiedemann model, which is at the heart of WISM. There is an implementation of the Wiedemann model from 1974 in SUMO as well, while WISM, of course, has a newer variant. In addition to that, SUMO has a very simple deterministic action step mechanism as well, which can be put on top of all the models. E.g., the time step is 0.1 second. The action step can be set at, for instance, 1 second, and the car following logic is then computed only at any 1 second, or if you use any larger values. If you do this without care, vehicles will crash. Anyway, the Wiedemann model in SUMO has its own action point mechanism, and action points are triggered when one of these 6 thresholds in the figures are crossed. Yeah, you see here they have very fancy names from SDV to CLDV, and they of course do very different things. So far for the theory, can we see them in real data? And of course we can, and many others have done so as well multiple times. So it might be wondering whether there are so little of those models in the model community. Anyway, in this case, data from the German SimTD project have been used which was a project designed to learn about vehicle-to-vehicle and vehicle-to-infrastructure communication, but not about human driving. But nevertheless, they measured the trajectories of about 100 vehicles driven by 1,000 volunteers from September to December 2012 near Frankfurt in Germany. The figure just displays one trip, and from these data we picked only those where the kinematic error was small. The error for the gaps must be smaller than 1 meter, and the one for the speed smaller than 0.25 meters in order to count as a valid data point. To learn more about action points, we analyzed the time series of the speeds in order to find them. We tried accelerations as well, but speeds work better. Maybe accelerations are too noisy. To actually find them is a small challenge, and we finally found two methods from computational geometry that worked very well. The figure shows the results for the two methods. One is the Rama-Douglas-Peuker, and the other one is the Wiedemann-Bayet approach, which is really hard to pronounce. You may have the feeling that the green lines, which is from the Wiedemann-Bayet approach, are a little bit better, and maybe they are, but of course this is a little bit a matter of taste. Okay, so big question: what is the distribution behind the distance in time between two subsequent action points? And in this case, we have found that the log normal distribution fits the best, but of course we have seen other data where a distribution is more appropriate. And it turns out that the average time between two action points is around 3 seconds, and just remember this number, while the modal value of the distribution is around, this is the value where the maximum is around 1.5 seconds. The interesting point with such a distribution is that it at least indicates, but of course does not prove, that action points are issued partly at random. So that does not mean that in all cases they are issued because there is a threshold crossed. Of course, even more interesting is the question of how the action points are distributed in terms of speed difference and distance. If perception thresholds are in fact used by drivers, then we should see them as lines in this figure. You can compare this plot here, which is the distribution of all the action points in car following from this SIMTD data, with the picture of the Wiedemann models, and here you see those thresholds which should have been visible in this figure as well. Okay, so obviously they are absent, and the distribution in fact looks very similar to the distribution of all the points from car following. This needs to be tested, and in order to do so, we resort to statistics. If one assumes that the distribution of action points is just proportional to the distribution of all the points, and this is exactly this equation here. This is the hatted h, which is, so to speak, our assumption that it is proportional to the number of to the distribution of action points of all the points as well. Then we can set up a nice simple test for that. That means we compare this hat h with the real distribution of action points, and this is just which has been named the Pearson residuals. I'll give you the equation in a moment. It's a little bit more complicated because it's divided further by the standard deviation of the h hat, sorry, but nevertheless, this is just a proportionality factor. Anyway, the interesting thing with these Pearson residual is if it is positive, that means if it is larger than 0, which corresponds to all the green boxes here, then it means that there are more action points than has been assumed by our simple model, and if it is red, then there are less action points than has been assumed by this simple model. And of course, if you sum it up and square it, then you end up with the famous chi-squared value, which can be used in the final test. So still, we do not see any thresholds, but what we clearly see is that there's a very nice pattern. And this nice pattern is that we have much more action points in the lower left and for small gaps here. and we have much less action points for larger distances, and for positive speed differences. So the positive speed differences are the one where the leading car is going away from us. So this is, in a certain sense, not completely surprising, but this is very consistent and very satisfactory. You may have noticed that this, and here is a proof in a certain sense, that this distribution looks very different from what can we get from the Wiedemann model. Here we have done not exactly the same setup as in the real data, but we have five cars following a lead car, and from that we can compute the action points and the distribution of action points in this car following space. You see there is a big difference between these Wiedemann model data and the SimTD data. In addition, we tested this one with another model, and that is the SUMO default model, which we endowed with a default action step length of 1.5 seconds, just to have another picture of that. Of course, this can produce, and it produces collisions, but nevertheless, we can still compute these resulting pattern. And again, it looks much more different than the real data. Yeah, if you look here. So in a certain sense, we have two models. These are these two to the right, and they are not in line with the real data. In the SUMO model, most of the action points occur here at small speed differences. Sorry, much less occur here at small speed differences, and more of them are in the outside. In a certain sense, this makes sense too from the perception from the point of the viewpoint of the model. So it's time for a few conclusions, and of course, one conclusion is very clear: the perception thresholds are a very poor description of the action point distribution in the SimTD data. It seems that real drivers do not use perception thresholds, which definitely is surprising. It is surprising because there is little doubt that humans have limits in perception, and for instance, how do you resolve very small speed differences, but they seem to manage without them. Of course, we have to note that other research have found some pictures of the perception thresholds, and you can see that here in these two plots on this slide. So maybe it's also a problem with our data analysis. Well, how could that be? And of course, the hypothesis that we are following now is that the drivers do not need the perception thresholds because they correct their acceleration anyway, any 1 to 3 seconds. So in a certain sense, they do so on a random basis. And sometimes, of course, it was necessary, and sometimes it was not. And so in a certain sense, they do not need any perception threshold in order to do their driving. From this, some future research directions can be stated. For instance, SUMO's modeling might be extended to allow for random action points together with a kind of testing mechanism. It means in each update step, one can compute a kind of test acceleration that is based on the model that is being used. And it is compared with the current acceleration. And only if this test acceleration is very different from the one that is currently employed, then the driver issues an action point. And so you came up with a kind of action point still, and kind of perception thresholds, or let's say thresholds, but they are much more complicated than the simple lines in car following space. Of course, it might be also a convenient starting point in order to find finally the still lacking crash model, but this is, so to speak, a very different point. Okay, that's it, what I would like to talk to you, and thank you for your